Hi everyone and welcome to video number 16, which is hopefully the last video of this series in which we are learning how to model an end plate steel connection. We are almost finished with the setup of this second version of this model in which we are considering solid elements in the bolted connections. So just to make sure that you have the same visualization set up that I have, select Abaqus deck here. Make sure that your pink buttons and yellow buttons look the same as in my ANSA. And in the draw mode, select property ID. And in the database, let's deactivate visualization of point, curve, and measurement. Now, the next thing that we need to do here is to finish the setup of the material. So open up material list. And for the bolt material, remember that when we deleted the beam element that were representing the bolts in the first version of this model, we applied a compress after that, and we end up deleting the bolt material. For this new bolt, I have created this new material, but I didn't set up this yet. So double click on this. And then to get information about this material, we can go back to the working folder. And then here we have the first model that we had run. I'm going to open up this .inp file, Ctrl F, and search for material. And then in here, I'm going to search for bolt material. And in here we have this information that we are going to use. We can do this in two ways. We can simply let this material definition, as you see here in ANSA, and then output this file and then edit the .inp file. So we would copy this information and paste it to the new .inp file. Or we could simply get, for example, modulus of elasticity, Ctrl C and Ctrl V here. Portions ratio is 0.3. We need to define plasticity. So plastic equals yes. Isotropic hardening, this is a monotonic loading condition. Question mark on data. We have these two tables, but we need to create a new one, new data table, delete everything here. The first point is this one for 0 plastic string. Next one is this one for this amount of plastic string. Press enter to insert a new row, and then next one is this one for this amount of plastic string. In plot, we can invert X and Y like this, and then you see that from here we have yield stress for 0 plastic string, and then we have strain hardening, and then after this point we have the material loses its stiffness. So we have an horizontal line. So we can increase. We are going to have an increase of strain without an increase of stress. This is likely representing the ultimate tensile stress. So after these, we have the ultimate tensile stress, which is like a limit for this material. So let's go back to properties. We can give it a name. So bolt material plastic, for example, click on OK, and then double click on this one that we have just created. And here we have the ID of this table. Click on OK, and we have just finished the setup. Make sure that you have everything defined here, because if you don't have it, you're going to notice that when you output the .inp file, the material that is not defined is not going to be written in the .inp file. Okay, so the next thing that we're going to do, which is something that is new and very important, is, let me just close this. Okay. In the Abaqus deck auxiliaries group, there is this tool here, control. Left click here, and then we are going to have a list of controls applied to this analysis. There is nothing here because we didn't create anything. So right click, new, And then I want to create a new control on the first step, parameter equals analysis, and analysis equals discontinuous. So let's understand what this means. First of all, you see that the command is asterisk controls. There is an Abaqus manual. I have it downloaded here, but you don't need to have the PDF downloaded. If you search, let me show here. It's here. It is the keywords reference guide. This guide here. If you search on Google Abaqus keywords reference guide, you're going to find the online version of it. And then in here, I need to search for Control F and asterisk control. And then I'm going to press enter again. And here we have it. Here we have information about this command. And what I'm using here is this option here. Analysis equals discontinuous. Discontinuous. And then if we have this analysis equals discontinuous, we set parameters that will usually improve efficiency for severely discontinuous behavior. We know that in our analysis, if we analyze the .inp file of one model that we had run previously, for example, this first model, I'm going to analyze the .sta file, and then you see that we have many severe discontinuities iterations, right? Here, and in many other increments. So this is our case. We have an analysis with many severe discontinuities, and then when we have this command, we are going to allow relatively many iterations prior to beginning any checks on the convergence rate. This means that we are going to allow the software to perform more iterations of equilibrium before giving up on that increment or before performing a cutback. You see that, for example, in this model, we have a cutback here, right? This cutback was performed after 4 severe discontinuities iterations. If we had this analysis equals discontinuous, probably Abaqus would have tried more iterations of equilibrium before performing the cutback. And you see that we have this word here, convergence rate, right? For every increment and for every iteration of equilibrium inside one increment, Abaqus analyzes the convergence rate. It analyzes the chances of converging that increment. If the chances are low while we are performing the iterations, then it's going to perform a cutback, right? So a cutback is performed based on the convergence rate. So if we ask the software to start checking the convergence rate later, then this means that we are going to end up having this cutback later. And this is good for a nonlinear analysis because sometimes we need to perform more iterations of equilibrium before giving up. Okay? Guys, for highly nonlinear FEA, like this one, this is a good practice. You should always use it. Okay, so we're going to define it for the first step, click on OK, right click, new, and also for the second step, analysis discontinuous, click on OK. All right, so this is a good practice. Okay, so material, this control. Now we can, before outputting the .inp file, let's use the compress function. Compress. Select detailed here to see what is going to be deleted. Alt X and check this box. And then scroll down and looks like nothing's going to be deleted. Okay, it's always a good idea to apply the compress function before outputting the .inp file. Now let's click on File, Output, Abaqus. And then before recording this video, I obviously have tested this model, and I have analyzed the errors and found the solutions. So this video is more practical. I know that this model is going to yield to an error. I want you to have the experience of getting this error and then fixing it. You see that I have already outputted this file here, v3. So in your case, you can output a file with this name, because we have a version, the first version and the second version, and we have this third version that we are creating now. So you can click on save, and then in here all, the version could be the last version, and then click on OK. In my case, I'm going to end up overwriting the one that I have created previously. And then to run it, copy the path to this folder where we have this .inp file, and then open up command prompt, cmd, press cd space Ctrl V the path, press enter. Now we are in that folder, and then copy the name of this file, Ctrl C, and then use the command abaqus job equals the name of the file without .inp, the quantity of CPUs, and then press enter and run it. I'm not going to do this because I have already run this module previously, and here I have the results. Notice that if I go to the STA file, in the first increment attempt of 10%, we had 2 iterations of equilibrium, and then the software noticed that the convergence was not, the chances of convergence was low because of some kind of error, and then we had a cutback. And then in the second attempt of this, so in the second attempt we had an increment of 2.5%, and then a cutback again. And then we had 5 cutbacks in a row. When we have 5 cutbacks in a row, Abaqus just gives up and aborts the job. And then it says the analysis has not been completed. When this happens, we should analyze the .msg file. And then here we have the .msg file opened, right? You should open this file here that is generated. And then in here we have, after this initial information, we have increment 1 starts, attempt number 1, 10%. Scroll down, and then we have this information here. Solver problem, numerical singularity when processing node with this ID. And then we have this warning happening for many nodes. For this node in these 2 degrees of freedom, and well, for many nodes here, right? And then after this warning, we have the equilibrium iterations. The residual force is very, very large. Residual moment is very, very large. Nothing converges. And so what we should do in this situation, we should search in the module this node, and also this node, and etc. So let's start with this node. I'm not going to search all nodes, because after searching the first node, we are going to understand what is happening here. So I'm going to Ctrl C the node ID, go back to ANSA, double click on node, and search for the node ID here, press enter, select this node, and then you see that looks like this node is positioned here. But there is one thing that is difficult in ANSA, which is if I zoom in here, you see that I don't have any more the node selected, right? So to facilitate our job to locate the position of this node, we can right click on this node and select reference. This tool is very important, guys. I use it a lot. This tool reference shows all entities that are somehow connected to this node. So in this case, I have 4 elements connected to this node. I can select these solid elements, and here we have a list of these solid elements. Now I can select one of these in this list and Control A to select everything. And then you see that here we have the element connected to this node. We have 4 elements that are part of the washer. If you continue searching for all these nodes, you're going to notice that all these nodes are part of the washers in this model. So, because of my previous experience running this kind of model, I know what is going on. When I started getting errors like this, I would have to investigate for hours and sometimes days to try to understand what is going on. But now that I have this experience, I know right away what is the problem that we have here. First of all, what is a numerical singularity? We know that when the stiffness matrix is singular, this means that we can invert it. Let me open board, and let me get the pen. This is really important. This is related to theory, and this is actually pretty simple. We know that we are trying to solve a problem like this, right? Stiffness matrix multiplied by nodal displacements equals to nodal forces. To find the displacement, which is our first goal, we need to pass the stiffness matrix to the other side, right? So we multiply, let me just move this more to the right. We multiply both sides by the inverse of the stiffness matrix, right? And then we know that the inverse of a matrix multiplied by itself is equal to the identity matrix, and the identity matrix multiplied by another matrix is equal to the matrix itself. It's like a unity multiplied by some value. Okay, so the result here is going to be the displacements is equal to the inverse of the stiffness matrix multiplied by the nodal forces. So we need to inverse the stiffness matrix to find the displacements. But when the stiffness matrix is singular, we can't inverse this stiffness matrix. So this is going to yield to a numerical singularity. A singular matrix is not invertible. This in FEA means that we have rigid body motion. Okay. So in the beginning of the analysis, the washer, we don't have contact occurring yet. We are going to start having contact, but in the first increment, we don't have it yet. So in the beginning of this analysis, this washer is floating, right? And then that's why we created this spring connecting the bolt to the washer. But the stiffness of this spring is very low, and we have connected only one spring. So I know that this is probably the reason why we are having this problem of singularity. And to fix this issue, we should simply create more springs to fix this washer in the beginning of this step. So let's do this. First of all, let's use the node function, this one. Select by property ID, select the washer, middle mouse button. Now I have the nut here as well. I'm going to press F1 to get this view. Use the node function again, but entity selection mode, create a box selection like this, middle mouse button. Now I have only the washer. Now I'm going to lock this view, and I'm going to use the first neighbor tool to show the springs. And then I'm going to double click here in springs, select all these springs, and right click and delete. Click on OK. And instead of connecting this washer to the bolt, I'm going to simply create in the Abaqus deck elements group, and then spring one node, and then I'm going to here in part and property we can select use existing, that's okay, and property could be use current. And then I'm going to select on this first washer this node here on this outer perimeter, on this side here that we don't have contact occurring, even though we have defined this whole surface as for the contact. In here we don't have contact because the bolt head doesn't go until this node. Mise en mouse button, and then first degree of freedom, spring X property, and then click on OK. Again on this node, second degree of freedom, click on OK. And here we have the correct property already. We can check it. Yeah, 15. Click on OK. And then Z direction. And then let's do this for this other node on the other side. Mise en mouse button, first degree of freedom, this property, second degree of freedom, this property, and third degree of freedom, and this property. Okay, we should do this for all washers that we have. I'm going to try to be quick here. Guys, one note here. These springs, we know that we are using it to stabilize the module, right? There are controls that performs this kind of stabilization automatically. But to be honest, I don't really like to use it because these controls, well, we don't have complete control of what happens when we have it activated. So I prefer to do this in a more controlled manner. And obviously that I'm going to remove these springs later. You can imagine that these springs is representing someone holding this washer while we have the bolt pretension being applied. Because, you know, in the real life, this actually happens, right? Someone needs to hold this washer, at least when we start applying the bolt pretension. Another thing that we can do in here to improve the convergence is to modify the gravity load. And we are going to end up learning about something that is very interesting. We are going to apply an amplitude to the gravity load. I'm going to show to you how to do this just well after I finish creating these springs. In this case, we need to perform this very manual work, but if we had done this before copying these washers, then we would need to do this only for one washer. Okay. We need to remember to include these new springs in the model change command for the second step to remove these springs. Okay, so let's not forget it. Okay, guys, we are almost finished. There is another error that we're going to get, and which is related to another thing that we need to fix. And it's going to be very interesting to fix this other error as well. It's related to the contact definition. So I have finished. Let's check one thing here. I have 6 springs per washer. So let me use the calculator. In total, we have 8 washers, right? So I should have 8 times 6 springs, 48 springs. So if I double click on spring and then create a box selection to select all springs visible, in this list I have 48 springs selected, which means that looks like it's correct. So this is one kind of check that you can always perform. Let's unlock this view, click in show all, and now let's open up step manager, double click here, and then on the second step double click, and then in model change, oh, there is nothing here. Looks like that one that we have created was not created. Maybe I forgot to click on insert. Before we need to create the set, so let's close everything, set list, right click, new, and then select spring here, select all springs visible. You see we have 120 selected out of 120. Check that you have everything selected. Middle mouse button, element set, and then these are the step springs. Click on OK. And now the set is here. Let me go to step manager. Step 2, double click here, output request, oh no, in the model change, and then say yes here, and then remove, and then question mark, search for the set, click on OK, and don't forget to click on insert. Now we have this item here, click on OK, and click on OK. All right, so we have the control discontinuous, material is set, is ready. We have the new springs. Now we can try to put this model to run, but I have done this previously, and let me show you what happened. I have run some tests here, right? In this first test, which is this model that we have here, this is what happened. Let me open the .sta file. So you see that it converges well in the first step. Actually, in the first increment, we have 38 equilibrium iterations, so it is very difficult to converge this first increment, but it converged. And then in the second step, we start with one cutback. And then the solver performs some increments, but another cutback. And then performs some increments and another cutback. So you see that it's being very difficult to run it. The increments are very small. And then we have so many increments here, and we are yet in 2% of load application. And we perform here 100 increments, and the solver stops performing increments because there is a limit established of 100 increments. This limit is established in the .msg file. So if we go to the .msg file, there is this information here, right here. The maximum number of increments in this step is 100. We can modify this, but it's not really worth it, because if we are having so much difficulty, this means that there is something wrong with our model and we should fix it. And I was thinking here that probably, and this is also from previous experience, if we try to analyze the MSG file, it's going to be a little hard to understand why this is happening. So this is actually something that you're going to develop with your experience. Sometimes you're going to face convergence issues, and you're not going to be able to fix in the same day. You need to sleep and think about it, and maybe on the next day you're going to have an idea, and someday you're going to fix it. This happens a lot. But when you get to fix it, you're going to memorize forever this kind of problem, and then on the next time you face it, you're going to know the answer right away. Okay, so in this case, I know that this is because of the contact formulation. we have used a small sliding tracking approach. But in this case, in these contacts that we have here between bolt and washer, washer and end plate, and etc., we are probably having we're not having small sliding, we are having finite sliding. So we need to change this tracking approach. To do this, let's go to contact, double click on contact pair. Let's expand this, and we have many contacts here, right? We know that this contact here, the first one between the end plate and column flange, converges with small sliding because it had converged on the first version, right? So this one, we don't need to change it. But the other contact, such as this one, double click on it. In here, in this field, small sliding, we should set it as no. And then we're going to use finite sliding tracking approach, which allows large relative displacement in the contact and separation and etc. Okay, so in this field, small sliding, we are going to set it as no. Click on OK. And we can open each contact definition and do it one by one, but there is a more practical way to do this. And this is really, really important, guys. Here in ANSA, you see that when I double click on contact pair, we have a table here, right? This is a table. It has two columns. The first column is ID. Second column is name. We can add more columns. To do this, click here, and then we can search for fields. These fields are, if I open up this card, these fields are related to each one of these fields that we have here. Okay, in this case, I want to add this field here. I'm going to Control C, and then in here, click here, search for this field, and then check this box. Now you see that we have this new column, right? Now, if I simply get this contact and uncheck this box, if I double click on this card, you see that I'm going to have a small sliding equals no, right? So this is very practical. So how do we modify this option for all these contacts except this first one? So select this, hold Shift, select the last one. So we have 24 selected out of 25. So we are not selecting this one. And then in this column, right click, modify, and no. Click on OK. And now it has modified all the contacts using one command. So after performing this modification, I tried to run this model again. And then here you have the STA file. And by the way, guys, in this first attempt, yeah, let's show this second attempt when I modified the contact. Let's see the STA file. Here we have it. STA file is here. You see that the first step converges pretty well. In the first increment, we have only 6 equilibrium iterations compared to 38. And then in the second step, it converges until the end, performing 71 increments. So it's not easy, but it converges. And we can, well, this was obviously related to the contact formulation, because I have changed only these. You can check, you can test it out, obviously. So you see that how a small thing in the model setup changes a lot the convergence rate in the model. I have here a meta with the results of these tests that I have run. So for this first one, that I had the wrong contact formulation, let me activate only this one. Okay, when we have many modules opened here in Meta, in this case I have 1, 2, 3, 4 modules opened. I can control which one is active by checking this box. So I want to have only this one active. And for this one, I have calculated avoidance stress on integration points. And let's see what happens. So we can see here where we are, step 1. And then here we have the end of step 1. So in here we had only bolt pretension. It worked. But then in step 2, we could apply, until the end here, we could apply only 2% of load, which means approximately 2 millimeters in the downward direction. And then it's not that it stopped converging, but it reached the limit of increments. Okay, we can amplify this deformation by multiplying this maybe by 50, and this is what is happening. So the model was working normally, but it was too difficult to converge, right? Looks like everything is working normally here, but it was too difficult. And then when I fixed the contact formulation, which is this model that we have here, you can run this model. The result that we get is this one here. Let me activate the second model, deactivate this one and activate this one. The result that I have here is what you see here. So you see that it worked normally, right? But there is one thing here. When I was testing these, I end up forgetting to define the material properties of the bolt. So we don't have plasticity occurring on the bolt. And you see that it deforms just a little. And we also have some penetration here. So maybe it's a good idea to define this contact. So let's do this. And in this video, it's pretty easy to define this contact. And then when I fixed the material properties, this is what happens. Let me activate this model now. Yep. This is what happens when we fix the material properties. We have this deformation occurring, and then we have plasticity occurring on this bolt. And then you see that we have a lot of deformation occurring here, because since we have the end of the curve of the bolt as an horizontal line, probably we have this whole section having a plastic strain in that region. So this means that the bolt is failing. And if we go to this to the article, we see that the failure mode of this model is because of bolt failure. So this bolt here on top fails, they separate. Okay. Anyways, we're going to analyze with more details this model yet. And here I have, yeah, no, this model is not important. So we need to do one thing here, one additional thing here. I need to create contact between, you see that in here we are having contact, right? Because in this model I have defined contact between the bolt and this hole. So let's do this, just so that you can learn about one additional thing. 38 minutes. Well, I'm going to finish this series in this video anyways, even if this video gets to if this video is 2 hours long, I don't know. Okay, so so far we have fixed the contact formulation to find it is sliding. We have also added these new springs to this model, and now we need to define a new contact. Let's just define this new contact for these two upper bolts, okay? Because let me see. Yeah, looks like it's only for these two upper bolts. Obviously, that this result is not valid. The result is valid up until maybe here. I don't know. Yeah, even here we don't have contact. But anyways, let's define this contact. in this third module, let me just show these to you. Let me activate this one. In this third module, I considered a linear bolt material, and I considered this contact here, just to see how this contact works. You see that we have contact and there is no penetration. Let's compare with this first module, actually this one. Let me activate this one as well. You see that in this case, since I haven't defined this contact, we have penetration. I can isolate this and this, and we can see there is some penetration occurring here because we didn't tell the software that there could be contact between these two entities. Okay. So here in Abaqus, first of all, this is going to be a different kind of contact. It is going to be a node to surface contact. So first of all, we need to create a set of nodes and then a set of solid facets. Go to set list, right click, new, go to node, select node here, and then let's select the loop selection mode, and then I want to select this loop of nodes. Okay, and here I also want to select this loop of nodes because I want to also consider that maybe we have contact here. Middle mouse button, this is a node set. We can just accept this default name, click on OK. Now right click, new, and then I want to create a set of solid facets. Feature area, 40 degrees, select these, and then I'm going to select all these solid facets. Okay, because the contact is between these nodes and these solid facets. Middle mouse button, and this is going to be surface. There is no need to define orientation because this is from a solid element and then element, and then click on OK. Now let's define this contact. In Abaqus deck, scroll down to auxiliaries tools and then contact. Left click and hold, select contact. And then in here, in the slave, so for this kind of contact, the nodes should be the slave and the surface or solid faces should be the master. Okay. And in here we should change to node instead of element. This is very important. And then question mark and search for the set. Instead of searching for this set here, just click on this node, and then it's going to recognize that there is this set related to this node. This set here, double click, and then question mark here, and then select this solid facet, and it's going to recognize that there is this set here. Double click, and then on the interaction, we can use the same interaction as the other contact, question mark, and select this one. And then just delete this because I don't want to use these options here, which is automatically selected. Small sliding, no, and node to surface contact formulation. So this is how you define a node to surface. You should select node here, and then in here, node to surface. In here, a node set, and in here, a surface. And in here, we have the iteration. Pretty easy, right? Now click on OK. And we should do the same thing for these other bolts. So let me do this fast. Create set node loop, this loop, and this loop. Middle mouse button, node set, click on OK. Create a new one, solid facet, feature area, this, middle mouse button, surface element, click on OK. Now search for contacts, search for the last created contact, right click and copy. On the slave, question mark, and select this node set, middle mouse button, and then on master, select this set, and then the rest we don't need to modify. Click on OK. All right, now we have these two contacts. where we are going to have contact. We don't need to define in other regions because we don't have contact. Now let me think here. Yep, that's all we need to do. Oh no, there is another thing that we need to do. Guys, this is very, very important. Let me isolate use the not function, isolate by property ID the bolt and the end plate, middle mouse button. You see that for the bolt, the sides of the elements are curved. Even though it looks like two straight lines, it's just the visualization of ANSA. This is actually a second order function here to represent this line. So this is a curve, right? And then we have many segments of curves, which is representing well a circle, right? But the problem is with the shell elements, because you see that the sides of the shell elements are straight lines, right? And this brings some difficulty in the convergence of this contact, and also the contact pressure distribution is not so correct when we have this kind of discretization. For node to surface contact formulation, the solver analyzes if the node, the slave nodes are penetrating on the master surface. And then we have only this node here, and then this node here, and then this node here, so it's discretized. So the stress distribution on the contact is not going to be so correct. And for that reason, we use a control here named as smooth surface. This is very important. I have shown this to you previously, but now we're going to actually apply it. To create it, we will need to create some points here to define the axis of these two bolts. In the database, double click on points, we have 8 points. I'm going to delete all these points, delete, so that we don't get confused. I'm going to the classic topo module, and then here points on COG, circle, and then the first point is going to be here. Select 3 nodes from this circle, middle mouse button, activate point visualization in the database, and here we have the first point. Do the same thing here. There we have it. Now the second point is going to be here. Select this node, for example. You need to select 3 nodes that is part of this circle. Do the same thing. Let me hide the end plate. And then select 3 nodes here. Now the point is created, but we can't see it because it's inside the bolt. Now in the Abaqus deck, auxiliaries, search for this tool here, surface smoothing. If you don't find it, you can search it in here, such as surface smoothing. Select this option, and then this opens up. The kind that I want to create is circumferential, and then we need to select the slave of the contact that we want to include. So click on show all. The slave is going to be question mark, zoom in and select this node set, right? Middle mouse button, and then the master question mark and select this surface, which is the master of the contact. And then we need to define point A, the X, Y, and Z coordinates of point A, and the X, Y, and Z coordinates of point B. These 2 points is to define the axis of this contact, because this is a circumferential contact and we have an axis for this contact, right? We can use those 2 points that we have created. So deactivate visualization of volume and visualization of FE mode. And now we can visualize these 2 points. To select the first point, select this field and then press F1. Select this point, and then the software is going to automatically define the X, Y, and Z coordinates of this point in this manner. Select BX1, press F1, and select this point, and then we have the X, Y, and Z coordinates defined here. Press OK, and then click on activate the visualization of these two. And then in here, inside contact, we have surface smoothing, double click on it, and then select it here. And then here we have how it's defined. You see that we have point A, point B, and then we have the definition of an axis, and then we have the slave and master. And well, this is going to facilitate the convergence of this kind of contact. And also it's going to represent well better the pressure distribution. Okay, let's do this also for the other contact. So again, search for surface smoothing, select here, and then slave is going to be this node set, mesomorph button, master, this one, mesomorph button, and then deactivate these, and then select this one, F1, select this point, select this field, F1, and select this point. Click on OK, and then activate visualization of these two kind of entities. And that's all. Let's save this. And now this module is completely finished. You can output this module and run it. Let me do this. I'm going to create version 4. Click on OK. Output all 2022. Click on OK. And in here, I have version 4. I'm going to put it to run. I have this command prompt here. Yep, this one. I need to run using this same command, but a version 4. Okay, so use a command like this and put it to run. Press enter, and then it's going to start running. Well, I have the results of this module as I have shown here in my meta. So guys, let me just close everything that I have here. While this module is running, I'm going to show the results of this module, which is, let me see here, which one is the correct one. I need to remember to show you how to open more than one module here in Meta. Let me see, maybe it's this module here. Yep, it is this module here. Okay, so let's just simulate, suppose that you already have, you put your model to run, and then you can stop the video, pause the video, and then when it finishes, you can return to this video, right? And then you're going to have the files of your model. And then in Meta, when you open up Meta in the geometry tab, firstly, we need to input the .inp file here. So let's search for the .inp file. I'm going to navigate to the folder that I have the files. I have created this additional folder named test. And in my case, I have this version 3 as the version that we are running there. So I'm going to select the .inp file. And then go to results. And in here, the software is going to recognize the .odb file with the same name in that folder. If in your case it didn't, so you should search for the .odb file here. And then in scalar, I'm going to calculate von Mises stress on integration points. And the rest, I want to calculate it for all states. We have everything selected here already. Deformation is going to be displacement, and that's it. In here, let's deactivate this option. I don't want to calculate vector result. There is nothing related to vector that I want to calculate, only scalar and deformation. And then you can click on read. It's going to start reading all increments. Okay, we can rotate this view, activate visualization of nodes by checking this option. Now we have the elements visible. And well, let's wait this to finish. And then I wanted to show you how to open two modules at the same time, so that you're going to have something like I have here. I have 4 modules opened here. Okay. All right. Now this has finished. Here I can move these like this to see what happens, and this is what happens, right? Now let's suppose I want to open another module in another tab here. First of all, notice that if I click here, I have only one module, and we have this checked, which means that it is activated, right? Now, if I go back to the geometry tab here and search for another INP file, you can do this for any .inp file, for example, of the first module that we have that we had run previously. Let me actually do this. Let me get here the first module, which is this one. Double click on the .inp file, and then we have this. In here, we need to choose this option, loading as a new module in new window. So new window, it's going to create a new window here with this new module without overwriting this one. Yes. And then this new window has been created with this new module that we have here, the beams, right? Again, check this to see the mesh and go to results tab, select integration point. And then in here, don't forget to check this box, because if I read these results, I don't want to overwrite the ones that I read for the other module. And then click on read. And then it's going to read all the results. And then you see that if I click here, I have 2 modules, right? The one with solid bolt and this one with beam element. Now I don't remember the difference between this one and this version 2. I don't remember what we have done here. Let me see one thing. This one ran until the end. This one didn't run until the end. I don't really remember. Oh yeah, the boundary conditions. We have considered some additional boundary conditions here. But let's consider this first module here, this first version, that we didn't have any kind of boundary condition applied here. So this node here can displace in the y direction and etc. And that's how we set up this second version, right? If we go to the step manager and second step, let's check the boundary conditions that we have here. We have 2. We have one here, which is the 200 millimeters displacement, and the other there, which is to fix these 2 displacements. So we don't have that boundary condition here to fix displacement in the y direction or anything like that. Okay. All right. It's almost finished. It's not finished yet. Let's just wait. Let's see here. This module that we are running, v4, let's check the .sta file and see how this is going. So you see that it has finished the first step. It was pretty easy to finish this first step. If we want to see here in Notepad++, If we want to see the real-time evolution of this file, we can click on View and then select this option, Monitoring. And then, well, let's. I'm not going to use this file here because it's going to take, I don't know, maybe 60 minutes to finish running. But everything is going well. Also, guys, let me show one thing here. This file here, version 3, is the same one that I'm running there, right? If we analyze the .msg file, where is it? Version 3. Yeah, this one. If we analyze the .msg file of this model that we are running there, you're gonna see that if we scroll down, here we have the where is it? Yeah, here we have increment 1, attempt 1. You see that we don't have any more of those warnings telling us that there is a numerical singularity, which means that when we added those additional springs, these solved that problem of numerical singularity for the washer. Okay, so you see that we don't have any kind of warning over constraints, numerical singularity, which is a good sign. Here we have the first equilibrium iteration for the first increment. The residual force is not so large, right, in the first increment, which is really good. Let me see one thing here, guys. Maybe I forgot one important thing. Oh yeah, I forgot about the gravity. I was going to apply an amplitude on the gravity, but you see that this is running pretty well, right? Even without applying this technique. So in theory, we don't need to do that, but I'm going to show you how to do that just in case you are interested, because this is really important. In this gravity definition, inside a load group, double click here, and then open up the gravity card. And then in amplitude, let's define a new amplitude. Let's select this field, use question mark. There is nothing here. We need to create, right click on new. And then we need to define a table here. So click on new, and then we have this table, right? So what is the meaning of this table? In the first column, we have this step. So here we have the beginning of this step and the end of this step, 100%. 1 means 100%. And here we have the gravity load. So in the beginning of this step, we have 0 gravity applied. And at the end of this step, we have 100% of gravity applied. And you see that in this chart, this gravity is increasing linearly when we have the increments of load, right? So we can change it. To change it, select this first row, right click and insert row below. And then what I want to do here is until 20% of this step, so type 0.2 here. So from 0 to 20%, I want to have 0 gravity, right? So a gravity started at 0 and it is equal to 0 for 20% of this step. And then from 20% until 100%, I want to apply gravity from 0 to 1, increasing linearly, which is what you see in this chart. This is how an amplitude works. It is very important to understand this because it's used a lot in advanced models. Okay, sometimes we need to do this. In this case, this would help, but it's not really necessary because we are this is converging without it. Anyways, and then we need to click on OK. And then here we have the amplitude created. We can close this, and then here we have this amplitude in this list. Double click, and here we have the ID of the amplitude. We can select it and press F2 to check this table that we have created, and then we can close, and that's it. Click on OK. So that's what I forgot to show. All right, I'm pretty happy, guys, because I end up teaching so much about so many things here about surfaces moving, node to surface contact, finite sliding, small sliding, these springs to stabilize the model. We have used many advanced tools here for nonlinear FEA. Here we have the model that we have uploaded the results that matters. You see that we have two results here. We have two windows, right? Now, if we click here, we have the two models, right? Only the end plate model is active here right now. We can control it by unchecking this box and then checking this one, and etc. So let's see the difference. Let's have this one checked firstly. Only this one. And then let's go to this window. This one is with the solid bolts, right? Now notice that in here, if I scroll it like this, I'm going to see the results of this model, right? Now, if I go here and uncheck this box and check this one, the information that I'm going to have here is related to the other model. So if I move this, you see that nothing happens with this model. We need to go to this other window, and then we can move it, and then we're going to have this happening with this model. Okay, we can also have the both models activated, checking these two boxes, and then it's going to be a little confusing here. So that's why I don't really like to do this. We're going to have the both models like this. We can go to this, and we have these two models like this. All right. So let's start post-processing these results. Let me see. 1 hour and 6 minutes. Guys, I'm not going to spend so much time here post-processing because we're going to simply do what we have done previously, right? First thing that I wanted to show in this new model is, first of all, deactivate the other model. Let's have only this one activated. First thing that I wanted to show is, you see that we have all these springs in here, right? If you're not able to see these springs, click on this light bulb. And then, first of all, you see that we have these surfaces where we have contact in these solid entities, right? I don't want to see these surfaces, so I need to uncheck this, surface from solid. Now I don't see any more of these surfaces. Notice the difference, right? I don't want to see the contact surfaces because it's going to hide the stress contour on these parts. Another thing is, in springs, you should have this activated to be able to see these springs. Now let me close these. Now notice what happens here. I'm going to start moving these to the right, and then on top of the screen we have where we are. So we are in the first step yet, 20% of the first step, bolt pretension, right? So let me move it like this. Now we are in 95%. Let me go one more. Now 100%. Notice what is going to happen with these springs in the second step. So I'm going to move one more, and the springs are removed because of the model change command that we have applied. Okay, now we don't have any more of those springs. We don't need it. This is important because this spring adds additional stiffness to the model, and which is not realistic. And then on the second step, we have this displacement being applied here, and then this happens. We start having this movement. But I have asked to calculate here von Mises stress on integration points, right? So in this scalar, let's choose on node, contour, and then activate the stress contour plot. First of all, let's use the node function and select by property ID this bolt mesomouse button. And let's go back here to ANSA material list And let's check the material properties of the bolt, F2 here in plastic. You see that, let me change here to 2 and 1. You see that in this region, the material loses its stiffness, right? We have an increase of strain without any increase of stress. And this happens for a stress equals 1160. So if we go back to META, we can set here the limit to be equal to that value, 1160. Press enter, right? When we do this, everything that is red in here has passed this region. So let me move it to the next increment and let's zoom in here. So it looks like there is nothing passing this limit yet. Let's go to the next one, and so on. Okay, now look at what is happening. We start having, let me check one thing here. Yeah, actually guys, we need to set this value here, 1160, press enter. Oh, so let's increase this to 1200, press enter, and this one 1160. Okay, well, this is odd because it's showing this color, and why this is actually happening here. Oh, sure, because we are never able to pass this value of 1160, right? The stress never increases more than that. So that's why, let's say 1159. Oh, okay. Yeah. Now we can analyze it better. You see that there is a moment. This is elongating a lot, and there is a moment here in this increment that we have this whole region with stress larger than 1159, which means that we are in this region here. So all this region in the bolt lost all its stiffness, which means that the forces that we have here in this region is going to be kept constant. There is not going to be an increase in force here. So then we're going to start having more increase of forces in this other region. When we go to the next increment, you see that we have a large displacement occurring here. And when we go to the next increment, these displacements are very, very large, which means that this bolt has collapsed. There is no stiffness anymore for this whole section. When we have this kind of plastic string occurring on the whole section, we lose all the stiffness, axial stiffness of this bolt. So this is like representing like if this bolt has separated in two. Okay, there is one way to insert a damage model here to actually have element deletion, but in this case, the author has represented the bolt separation when we have the whole section with in this region here. So we have lost all the stiffness of this bolt for this whole section. Okay. The same thing is happening for these bolts. And now if I go to this file, let me see. I'm going to open this one that has experimental data. You see that in this file, our model is this one, EPC1, 20 millimeters end plate thickness and 20 millimeters bolt diameter. In the case of this other article that is related to the simulation, we know that our model is SC2, but in this one, our model is EPC1. If we scroll down, we have this table here that shows the failure mode, bolt fracture. Okay, And then we have a picture here of EPC1 related to failure modes. And then you see that these bolts here, these bolts in this region doesn't exist. So these bolts separated in two, we had failure of these 4 bolts here, while we yet have these bolts in here. Okay, which is what is happening in this model. We have these 4 bolts failing, and these bolts are yet here. Okay, so this model is representing pretty well what's happening in reality. And what happens after this? You see this elongation. This is not realistic. It's in the software we don't have the setup of separation here, and what is happening here is not really realistic. Okay, we can imagine that we don't have anymore these 4 bolts acting. I'm surprised that this has converged, because notice how the elements get distorted. We are having an increase of this length without an increase in force. So it's not like this bolt doesn't exist, because we have some constant force here. So we yet have some force that is not realistic acting on this module. So what happens after this is not realistic anymore. So we can consider only the results of this analysis up until maybe here. Because in the next increment, we have this one with this kind of plastic strain through the whole section. Okay, so up until this increment, the results are valid. So I'm going to show all, and we are at this stage. This is the last moment that we have this model as a valid model. All right, let me think here what I need to show to you. Let's extract the force versus rotation curve. By the way, guys, if you want to have this scale in auto range mode, you should right-click, select linear and auto range. And then it's showing here the stress. This large stress is probably in the nut or washer, because we didn't define plasticity for these modules. So this is not realistic. If we hide, let me use not function, select by property ID, select one washer, it's going to hide all washers and nuts. And then we have this high stress here, which is occurring in the bolts. You see that this maximum stress is 1150, which is very near to the maximum that we can have. Okay, so we are almost in the limit of these bolts. All right. And by the way, this is for, we can see here, this is for 40% of displacement. So let's extract the moment versus rotation curve. Let me open up this Excel spreadsheet that has the results of the other module. This green curve here is for when we applied those additional boundary conditions, right? Guys, I'm not going to do this in here, but you should perform the verification of this BVP. You should check if the sum of all forces is equal to 0 in all directions. Okay? It's very important. You should always do this. But to save some time, since you know how to do this, I'm not going to do this again here. So let's go to curves, search here for the file. And then I'm going to search for this last one. Oh, actually, this one is running yet. So I'm going to search for the one that I have run previously, which is this one, 3. So we need to search for the ODB file. This, in my case, it's this one. Double click, and then we're going to access the history data. And then in this set, measure rotation, which is a set that has a node here. We can select here. Let me check one thing here. Guys, I just thought about another reason why we are having a difference between our curve and the test curve is how this rotation is measured, because we are measuring it by calculating the rotation of a node in this region, right? I don't know how this was measured in the experiment. Maybe it was in a different manner, and then this is one of the reasons why there is this difference, right? So measure rotation about y-axis, read. Now go back to read results, curves, displacement node. This is a set that has this node right here. I want to calculate reaction force in the z direction. Read. Now I have these two curves. Go to plot list. I have these two curves, right? I want to create a third curve using the information of these two. So calculate curve functions. I have something here, but let me set up it from scratch. So for this new curve in the x-axis, I wanted to have rotation. Rotation is in this first curve here. So select this first curve. And then in these three dot expressions, I want to get the y result of this curve that has rotation, right? Because the x result has time or pseudo time here in a static analysis. And then in the y-axis, I wanted to have this force, right? Select here, this reaction force, three dots, expressions, C2y. But I need to do what we have here. I need to multiply this by 1.2 to transform it to a bending moment, because it is the force multiplied by the distance, which is 1.2 meters, and divided by 100, because in this curve that we are going to use here, we have kilonewton times meter, and I have force here in Newton, so I need to transform it into kilonewton. So multiplied by 1.2 divided by 1000. And we need to consider a minus sign here, because I want it to be a positive. I want these two to be positive, but it is naturally negative. Apply. Close. There is this new curve, right click, show only, and this is the result. So we have a linear behavior, kind of linear behavior here, and then material plasticity occurs, and then probably here we have the bolt fracture when we when we have this loss in stiffness. I'm going to double click here, and then I'm going to go to edit, and in this table I'm going to Control A and Control C all this information, move to the Excel spreadsheet. I'm going to paste this table here. Okay, now I'm going to insert this information in this chart. So let's do this. I'm going to select this chart, right click here, select data, add, and then as the x-axis, I'm going to select this first column until the end. And then on the other axis, I'm going to select this other column until the end. Click on OK and click on OK. Here we have the first, the new data. And look at, this is very interesting, because you see that this is very near to the, well, no, it's not very near. It's near to the simulation that was performed by the author of this article. You see that this dashed line is his simulation. This gray line here in my case is this curve that we have just calculated. So there is some difference between our first model and the second model. And then in here you see that when we start having a negative stiffness, that is when this inclination of this gray line starts getting negative, is when we have the bolt failure of the experimental data, which is this continuous black line, right? You see that this new data, this new table curve that we have calculated has less error if compared with the experimental data results, which is this black continuous line. We can hide these two. Let me select data and let me uncheck these two. Click on OK. Oh, okay. We need to adjust this scale probably. In here, it's not possible to see so well, but I need to format axis. And then in here, we need to go from 0 until 400. Press enter. Yeah. And in here, 0, 0.02, it's correct. Okay, now it's better. You see that now this model is representing even better this curve using solid elements in the bolted connection. The difference here is very. Let me change maybe the color here so we can see it better. Format, and then in the line color maybe red. Yeah, and then in the markers also red. Okay, so you see that this is representing very well the experimental data. So we can say that this model is validated. This model actually represents the physical problem that we want to solve. Okay, and it represents very, very well. Okay, so this is one thing that we need to do. Let me return here. Guys, let's see how this bolt pretension works. Let me click on show all. And now let's see how this bolt pretension works. You're going to see that this nut moves to the left. I'm going to use the nut function, PID selection mode, select bolt and washer, mise en mouse button. I'm going to return to the beginning of this analysis, press F1 to get this view, or actually F2, F3, yeah, F3. Zoom in here, and let's see what happens in the first step when we have bolt pretension. Let me zoom in this region, and then notice what happens with the nut. Or actually, the nut doesn't move, actually the bolt moves to the right, because we have contact here, which is preventing this nut to move to the left. But we can, to facilitate this visualization, we can amplify this deformation by maybe 10. Press enter, and then let's see. You see, the bolt is moving to the right, which is the correct behavior that we wanted to represent, right? In this model here, I have von Mises stress on integration points. Now let's see how we would analyze this bolt here in this. I remember that I mentioned you that in this model, since we don't have the threaded region represented, I'm not going to analyze the threaded region. And also we should be careful with, let me hide the washer. I don't want to analyze the stress in the washer. This is a commercial item. So I'm going to hide the washer. Oh, actually, let me Control Z. And I want to select by PAD region, select this washer and mise en mouse button. We have a stress singularity here, right? We have this this corner with radius equals 0. So we should be careful with the stress calculated in this region. Okay, it's usually larger than the real stress that we would have here, because in reality we have a small radius here. But if we want to represent this small radius, then we would have to consider very small elements here. So it's usually not worth it. So when we are analyzing a bolt, we should analyze this region that starts here in this first row of elements and end here where we have the start of the thread. I don't know. Let's suppose that the start of the thread starts here at this layer of elements. So what we can do here is I'm going to use the not function. I'm going to select entity selection mode, create a box selection. You see that I have this view that has nothing behind. I'm going to get a view like this, use the left mouse button to create a box selection, selecting these elements here. Middle mouse button. And then here we have the elements that I want to actually analyze the stress in this bolt, right? In the scale, right click and in range options, select, instead of visible parts, select visible elements. So I want this scale to be adjusted to the visible elements. Now, let's see, the yield strength of this bolt is equal to 990. So when we have bolt pretension, we have this the length of the bolt increasing, obviously, right? Because it's being subjected to a tensile load. Probably we can also visualize that because of Poisson's ratio, the diameter is decreasing. Let's see. Yeah, notice that we have a decrease in the diameter. We can even amplify this deformation more to see this effect. And this is one kind of nonlinearity that is occurring. Let me amplify this to 100. Notice that the diameter decreases, right? Because of Poisson's ratio. We can easily see this here. Cross-sectional area is decreasing. And this is a large deformation nonlinearity that is occurring. And Abaqus takes this into account because we have that option here in step. Let me show to you. In the step definition, we have in LGM equals yes. So we take into account large displacements and deformations nonlinearity. Let me go back here to multiplier equals 1 to see real deformation. So let's analyze here the maximum stress that we have occurring here. Let's suppose that we establish a limit of 990, which is the yield strength. So let's continue. And then you see that in this increment, we have this region here and this region here with starting to yield. Okay, so we start having plastic strain here and here. So if we say that the acceptance criteria for this bolt is yielding, so we say that we cannot have yielding occurring, and we have a ductile metal here, and then we can use the von Mises stress. We can use the von Mises yield criterion. Then we can say that in this increment, this means the maximum displacement that we can have. We can read here that this is for only 7% of the second step. We can calculate, we have a displacement of 200. So 200 multiplied by 7%, 0.07, is equal to 14 millimeters. So we can click on show all, and let's analyze what is happening here. So when we have this displacement here of how much it was? Yeah, I forgot. When we have this displacement here, then we have yielding starting here. Okay. But this is only for when we have this acceptance criteria. We can allow some plastic strain in the bolt. Sometimes we allow it. It depends on the condition. Okay, sometimes we allow some plastic strain. All right. So guys, another thing that I wanted to point out is that sometimes, I don't think this is so correct, but sometimes some companies just ignore this layer of element because of this stress singularity. Or there are other companies that considers an analytical model that can predict the stress that we would have here by having the stress in some previous layer. There are some techniques like this. Or you could simply represent this curved, this fillet that we would have here, which is not really so practical. Okay. All right. Well, you can perform the same kind of analysis of stress for the other components to see. You can establish what is the quality criteria, no, the acceptance criteria, if it's yielding, and then you can isolate, for example, the beam with the end plate, and then you can analyze what is the displacement that we can have so that we don't have yielding occurring. For example, you can perform this kind of analysis. Okay. Okay. Let me think if there is something else. We have 1 hour and 35 minutes. Oh my god. If you are watching this until this point, then probably you are very tired, but you have learned a lot, right? You can compare the oh yeah. Okay, so now that we have these bolts as solids, we have this stress distribution in this region of the end plate. And in here, well, this stress distribution is more accurate. Also, guys, let me show here, when we have more displacement occurring here, you see that we have this contact occurring here, right? We have some penetration because this kind of contact, we know that it allows some penetration. This is a penalty-based formulation. So it's like we have some normal stiffness in the contact, and we have some penetration occurring. Another thing that you can do is to calculate in scalar results. Scalar, you can calculate a stress, contact pressure, for example. You can calculate it, analyze the contact pressure, and compare with the results that we have here. We have these two pictures. You can compare it. Also, this one, I have taught how to do this previously, so I'm not going to do this again. Let me see this model that we are running. Oh, it has finished already in this case. Okay, so it finished, so it's working, and the results is exactly these ones that I have shown here. Okay, there is just one last comment. I swear that this is the last comment, and this is very, very important, guys. This is what I was forgetting to tell you, and this is the last information. You see that in this module, we have shell elements, right? For the end plate, for the column flange, and we have compression occurring in the end plate because of bolt pretension, right? I'm going to isolate the end plate, and there is going to be this region of the end plate is being compressed because on this side there is a force to the right, and on the other side there is this contact between the column flange and the end plate, and then because of that this region of the end plate is being compressed. The stress distribution that we have here when we have a shell element being compressed is not so good. It's not so realistic. Okay, so this stress that we are having here is not so realistic. I know that because I have written recently an article that compares this stress distribution in this region when considering different kind of elements. And I'm not going to show this study. I'm just maybe I'm going to show one picture that I have here. let me see if I it's not this one. Yeah, I have some images of this model here. You see that in this model I have one model that I have this kind of compression considering solid tetrahedron elements, solid hexahedron elements, and then in here I have shell elements, and then I have this continuum shell element, which is a special kind of element that has this nomenclature. And then I noticed that only when we have solid elements, tetras or hexas, we have a correct representation of the compressive stress that we have in these two plates in this region. So my point is, if you need to have a correct representation of this stress, then it's worth using solid elements for the end plate and for the column flange. Okay. All right. This is my last observation about this module. Congratulations if you watched this series until this point. I hope you have learned a lot. And this is just the first tutorial that I'm creating. There is going to be other tutorials like this. And yep, so I hope you liked it, and see you in the next tutorial.